Hey everybody, welcome to my guide to understanding and implementing the groundbreaking image generation deep learning model called StyleGAN. In this guide, you will find everything that you need to know in order to implement this model by yourself. Before we move on, here is what you'll need in order to understand the material covered in this guide. For each of those subjects, I will give a general recommendation on where to learn it if you need to. First, you'll need to know to build basic plain GANs. There are some great YouTube vids for that, just do a quick search. You also need to be familiar with WGANs with gradient penalty, a midway level GAN model. I made a video all about it, so check the link in the description. Obviously, you'll have to have skills in using PyTorch, since this is the deep learning framework we will use. Two additional subjects I will mention during the video is broadcasting, which is explained quite well in the NumPy documentation, and batch normalization, to which I will link in the description, a guide I found well written. With all of that in mind, let's begin, shall we? As I said, StyleGAN is another step in developing better, stabler GAN models. Between WGAN and StyleGAN, there is another step, called progressive GAN or ProGAN, which I will cover. The central idea of ProGAN is to train both generator and discriminator in gradually increasing resolutions to provide the network the ability to learn lower level structures first and finer details later. For example, the generator can learn to place the eyes in the right place and make them circular before having to learn to paint the eye hole and eyelashes. Now, allow me to explain the architecture of this model. We start by generating noise and converting it through a convolutional layer to size of 4x4. Then this is passed to a discriminator that tries to figure out whether what it sees is real or fake, just like any other GAN. When we are done training this resolution, we can increase it by a factor of 2 to 8x8 and continue training. This process can go on to 16x16, 32x32, and so on. Now I will focus on exactly how this works by zooming in on part of the model. As you can see, each resolution of the generator adds another convolutional layer that converts the information from lots of feature maps into an RGB image. Similarly, the discriminator has a convolutional layer that takes that RGB image and converts it into lots of feature maps. The idea is to train one resolution until it is doing a satisfying job, and then move on to the next resolution. I should now talk about the idea of fading in and fading out, which is used to make the transitions between different resolutions more stable. Let's say that we are now training the 16x16 resolution. The data is processed in the appropriate convolutional layer, converted to an image, back to feature maps for the discriminator, and down the model until the final prediction. Now we start training the 32x32 resolution. The height and width dimensions are multiplied by a factor of 2, the data goes through another convolutional layer, converted to an image, and moving into the discriminator. But apart from that, the information takes another route that bypasses the 32x32 convolutional layer and goes straight into the RGB layer. In the beginning of this resolution's training, this route is the dominant one, and slowly there is a transition to the route through the convolutional layer, a transition that is controlled by a parameter called alpha. Personally, I did not use this mechanic and instead opted to train the new layer while freezing the previous layers for few batches before training the whole network again. This worked well for me and was much simpler to implement. But if you want to learn how to do it anyway, there is a link in the description to a progressive GAN code walkthrough by Aladin Persson, which is a great watch. Now that we understand the basic of progressive GAN, we can move to StyleGAN. There are two major changes to this model, and some smaller ones that I won't cover here and you can read about in the original paper. The first of those changes is that they move the latent code from the beginning of the upsampling process into the normalization functions all across the generator. This allows the network to learn high-level and fine-grained features separately. The second is adding a random noise to the feature maps. This allows for even more variation and diversity in the generated images. We will go into more details during the next slides. Okay, so let's see how to implement this thing starting from the basic convolutional block. In the init function, apart from defining the layers, there are a few ideas to note. The arguments are the number of channels going into the block, the number of channels coming out of it, the number of hidden channels, and whether or not it should upscale the height and width dimensions. I gave some torch functions a more specific name depending on what they are doing in my code, but this is just semantics. And here is the noise factor that worked for me. We will soon see where it fits in the code. Now let's talk about the forward function. First, we upsample the data if we need to. We apply a convolutional layer and activation. Here I chose Silo, which works well here for me. We generate noise and add it to the information. Here, the noise factor comes in and makes sure most of the information is still viable and is not obscured by too much noise. The information goes through adaptive instance normalization. Soon we will explore it in detail. And the whole process repeats itself with new layers. Now it's time to talk about adaptive instance normalization. Just as batch normalization makes sure each feature map has the same mean and standard deviation all across the batch, adaptive instance normalization makes sure there are certain mean and standard deviation to the feature map, but this time regardless of other examples in the batch. You can see how the n dimension, which stands for the batch, goes away. So, the way we inject randomness into the generation process, thus creating different images each time, is that we start with some noise, normalize it, pass it through 8 fully connected layers network, and the output is used to determine what will be the mean and standard deviations of each feature map. That's the adaptive part of adaptive instance normalization. To implement this network, I just defined in the Conv Block init function a submodel that consists of 7 fully connected layers in a row, followed by 4 different heads. 2 for the mean and standard deviation of the first adaptive instance normalization of the block, and 2 for the second one. So, how does the adaptive instance normalization function works? It receives the input to be normalized, whether it's the first or second normalization of the block, and if needed, an external noise. If no noise is given, we generate one here, and pass it through the fully connected first 7 layers. Then, depending on the iteration argument, we use the appropriate output layers. We add 2 dimensions to the output so we can later use broadcasting and calculate the mean and standard deviation across the height and width dimensions. Then we subtract the mean and divide by the standard deviation to make sure the new mean is 0 and the new standard deviation is 1. Lastly, we scale and shift the information based on the output of the network. Now let's tie this all up in a generator model. The initial value is a learnable parameter that will get updated. And it's important to use a single dimension for the batch size here and repeat the tensor later to make sure all of the initial value is the same across the batch. The forward function goes like this. The only argument is which resolutions we want to produce. From the resolution, we can calculate the number of layers to use, and we repeat the initial value to match the batch size. We clone it, so we can use the same value in the following for loop, and use the conv blocks we defined earlier. If you are wondering, yes, the gradients do flow through cloning to the original tensor, so it can be updated. Then, the matching RGB layer is used and the generator is done producing the image. Now, let's look at some results. Here you can see how the outputs are growing from 4x4 to 8x8 to 16x16 to 32x32 and finally 64x64. But you can take it further if you want to. Here, I tried to give you a taste of all of the range of image qualities I got. I'm pretty sure the network just needs a few more days of training to get more consistent results. Here, we can see what changing the normalization values at only a single resolution affects. The lower resolutions affect general structures of the face. The 16x16 resolution learned to not affect anything apparently, and the 32x32 resolution affects fine attributes such as hair shape, eye shape, skin tone, and more. The 64 resolution learned to affect the color of both hair and eyes, which I think is pretty cool. Lastly, here is the result of taking the low-level attributes from the left image and the high-level attributes from the right one. We can see that we get an image that resembles both of them. That's it for the guide. I hope you learned and had a pleasant time. I plan on posting more guides in the near future, so feel free to subscribe to get notified. Thank you and see you soon.